You know that feeling when you're trying to grasp a really big, complex idea, something fundamental, like the very laws that govern our universe? For a long time, physicists have been chasing one grand answer, one ultimate equation, a theory of everything, designed to unite all of physics. It's been the holy grail. But what if that's not how the universe works at all? What if, instead of one single ultimate equation, reality is more like, well, like a cosmic symphony, with distinct instruments playing together in harmony?
Indeed, that's a great way to put it. Our source material today, primarily a groundbreaking paper titled Symphonic Physics, Theory Refinement by someone named A. Allister, introduces exactly this kind of novel framework. It's called the Symphonic Theory of Physics, or STP for short. And it suggests a really profound philosophical and mathematical shift. It moves away from strict reductionism, the idea that you always drive one theory from a more fundamental one, towards a model of what the paper calls intertheoretic coherence.
Intertheoretic coherence.
Yeah. It proposes that our two most successful physical theories, Einstein's General Relativity, GR, and the Standard Model of Particle Physics, aren't just waiting to be subsumed into some single grander theory. Instead, the idea is they are fundamentally distinct, but interact in specific, defined, and, well, profound ways at critical boundaries in the universe.
Okay, let's definitely unpack this because that sounds like a major shift. Our mission today, then, is to dive deep into this symphonic theory. We'll explore why a radical new approach is even needed, how this theory actually works, what colossal problems it claims to solve, and crucially, how we might actually put it to the test. Is that possible?
That's the goal, and the paper argues it is.
Think of it maybe as a shortcut to understanding a potential paradigm shift in fundamental physics, a way to listen to the universe not as a solo performance, but as an orchestra, and maybe discern the laws of its cosmic harmony.
Precisely. It's about listening for the interplay, not just the individual notes.
And we have a fascinating set of sources that really pull back the curtain on this, don't we?
We do. It's not just the main paper by A. Allister laying out these foundational principles. We also have the peer review correspondence.
Ah, the good stuff, where the debates happen.
Exactly. The lively, sometimes quite passionate, peer review debate it sparked. We get to see the critiques, the endorsements, the suggestions.
And the author's response to all that, it gives a really transparent view of how a potentially radical new scientific idea starts to, wow, make its way.
And there's also a public explanation mentioned, one that uses this symphony analogy quite effectively to make these incredibly complex ideas more accessible. So we get the science, the debate, and the explanation.
Perfect. Okay, let's start with the why. Why do we even need a new tune in physics? What's the cosmic discord this theory is trying to address?
Right. Well, for decades, the brightest minds in physics have been driven by this powerful, unifying impulse. It's this grand quest, you could say.
Like composing that ultimate symphony, right?
Yeah.
Describing every note, every instrument, from the tiniest vibration to the biggest galaxy cluster.
Exactly. And to be absolutely fair, this approach has yielded incredible successes. You just have to look at the Standard Model of Particle Physics.
Which is just brilliant for the quantum world, yeah.
Absolutely brilliant. It successfully unified 3 of the 4 fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, into one coherent quantum field theory. A real triumph of that reductionist approach.
Showing its power, for sure, but there's always a but.
There's always a but. And the but here is gravity. While the Standard Model elegantly handles those 3 forces using quantum fields, the 4th force, gravity, operates on a totally different conceptual stage. Gravity, as described by Einstein's General Relativity, isn't just another force mediated by particles in the same way. It is the large-scale structure of space-time itself. It's the geometry.
So 2 incredibly successful theories, but ruling different domains.
Precisely. The Standard Model nails the microscopic realm of particles and forces. GR accurately describes everything from planetary orbits to cosmic expansion, even black holes. Incredibly successful, each in its own domain.
But bringing them together, that's the problem.
That's the problem. Trying to find that single unifying theory of everything, or TOE, that accounts for all 4 forces, has led to this profound and, frankly, persistent schism in physics. It's like having 2 perfect musical scores, masterpieces on their own, but written in different languages, different notations. They just don't seem to fit together into one grand opus.
So this isn't just a minor disagreement about some calculation detail?
Oh, not at all. It's a deep philosophical divide, almost a cultural one, within the physics community, like 2 rival schools of music that can't agree on the fundamental rhythm of the universe.
And this leads to the different camps, right? The stringy people and the loopy people.
Ah, yes, as one of the reviewers rather colorfully put it. It's a fairly accurate, if informal, description. They have their own conferences, their own research directions. Sometimes, sadly, even those bitter, vicious public arguments the source mentions.
Okay, so what are the two main schools? String theory is one.
Right. String theory is hugely ambitious. It posits that the fundamental constituents of reality aren't point particles, but tiny, vibrating one-dimensional strings. Different vibrations correspond to different particles. And the big hope is that it naturally includes gravity, the graviton particle, and unifies all the forces. A theory of everything.
But it comes with some conceptual baggage, doesn't it?
It does. A hefty price tag, you might say.
Mm-hmm.
Things like extra spatial dimensions, maybe 6 or 7 of them, curled up incredibly small so we don't see them, and supersymmetry, or USY.
It's USY, where every particle has a heavier superpartner particle, which we also haven't found yet.
Exactly. Lots of theoretical elegance, but requires these quite speculative ingredients that lack direct experimental evidence so far.
Okay, so that's the string camp. What about the loopy people? Loop quantum gravity.
Loop quantum gravity, or LQG, takes a different tack. It's generally more focused. Its primary goal is to quantize gravity itself, directly applying quantum principles to space-time geometry. It doesn't necessarily aim to unify all forces from the get-go, though compatibility is hoped for. Its core idea is that space-time isn't a smooth background.
It's discrete, like pixels on a screen.
Kind of like that, yeah. It sees space-time as woven from fundamental loops or quanta of gravitational field, forming a sort of quantum network, a granular fabric at the Planck scale. And a key difference is that LQG typically doesn't require extra dimensions or supersymmetry. That's often seen as a point in its favor, fewer unproven assumptions.
So the philosophical difference is pretty stark then.
It really is. String theory asks about the objects within space-time. What are the fundamental bits of matter and force? LQG asks about the quantum nature of the space-time stage itself.
Wow. Okay, not just what's in the universe, but what the universe is made of at the most basic level.
Exactly.
Yeah.
And the fact that these two major research programs have coexisted for decades, often without much productive interaction, that persistence itself suggests something.
Suggest what? That maybe they're both wrong, or?
Or maybe that the fundamental premise, the absolute necessity of a single unified theory that reduces one to the other, might be the actual stumbling block.
Yeah.
Maybe we've been trying to force two different kinds of music into one score when we should be figuring out the rules for their duet.
Which leads us to a really uncomfortable point for both camps, the untestability problem.
Yes, this is a growing concern. After decades of brilliant theoretical work, enormous intellectual effort, we're kind of at a stalemate.
The Cosmic Orchestra has these two amazing sections, the strings and the loops maybe, but they can't play together. The conductor has no score, and worse.
Worse, the unique music they predict, their specific distinguishing features, are often predicted to manifest at energy scales so high or in ways so subtle that we simply can't detect them with current or even foreseeable technology.
So we can't even tell if they're playing the right tune.
Precisely. And this raises a very serious question. If a theory makes no testable predictions, or if its predictions are perpetually out of reach, can it truly be considered empirical science?
That's a heavy question.
It is. And both string theory and loop quantum gravity, for all their mathematical beauty, struggle with this. For string theory, the characteristic energy scale is the Planck energy. That's 10 to the 19 GeV.
Which is enormous.
Staggeringly enormous, about a quadrillion times more energetic than the Large Hadron Collider can reach. We're talking energies that likely only existed fractions of a second after the Big Bang. We can't build an accelerator anywhere near that powerful.
Okay, so direct tests are out for now. What about indirect predictions?
Well, that's where the other problem comes in. String theory's low-energy predictions depend heavily on how those extra dimensions are curled up or compactified. And it turns out there's a colossal number of ways to do this, leading to the infamous landscape problem. Maybe 10 to the power of 500 possible vacuum states, each corresponding to a different universe, with potentially different physical laws.
10 to the 500. That's not helpful for predicting our universe, is it?
It makes specific, falsifiable predictions extremely difficult, to say the least. It's like having a theory that can predict any outcome, which means it predicts nothing uniquely. Like that music that can only be heard by an imaginary instrument, and even then it could sound like almost anything.
Okay, so string theory has testability issues. What about loop quantum gravity? Didn't it have some promising testable predictions initially?
It did, yeah. LQG was championed for a while for potentially testable predictions, particularly the idea of Lorentz invariance violation.
Meaning the speed of light might not be perfectly constant?
Exactly. The idea was that space-time's discrete, granular nature at the Planck scale might affect the propagation of very high-energy photons. Maybe high-energy light travels slightly differently than low-energy light. If true, we could detect this by observing gamma-ray bursts, incredibly energetic explosions from distant galaxies. Photons of different energies are emitted simultaneously, so if they arrive here at slightly different times after traveling billions of light years.
That would be evidence for LQG's granular spacetime. Did we see it?
No. Increasingly precise astronomical observations, especially from satellites like Fermi, have looked very carefully for this energy-dependent speed of light from gamma-ray bursts, and they haven't found any evidence for it.
Ouch. So that prediction didn't pan out.
It didn't, and this has placed severe constraints on the simplest, most predictive models of LQG. While proponents argue the theory isn't entirely ruled out and doesn't absolutely require this effect, losing a key potential empirical anchor was a significant blow.
So both major approaches are struggling with empirical verification.
They are. This shared drift away from experimental testability, this widening gap between complex theory and achievable measurement, has led to what some call a crisis of confidence in fundamental physics. Critics, and even some insiders, worry these fields might be becoming more like philosophy or mathematical explorations than empirical science, surviving, as one quote puts it, on little more than passionate advocacy.
Which is exactly the opening for a new idea, like the Symphonic Theory of Physics. It's stepping into this stalemate.
Precisely. It aims to offer not just a different conceptual framework, but, crucially, a framework with potentially testable consequences right from the start, shifting the focus away from the inaccessible Planck scale.
Okay, this is where it gets really interesting, as you said, the symphonic vision. How does it propose to change the tune?
Well, the core idea of the symphonic postulate is a radical departure. It says,
Yes.
stop trying to replace the orchestra with one super instrument. Stop trying to force the cellos and violins to play the exact same part. Instead, embrace the orchestra. Except that the universe might not be a monolith described by one ultimate theory. What if reality is fundamentally pluralistic?
Pluralistic, meaning multiple fundamental theories coexisting.
Exactly. STP proposes an ontological pluralism. It suggests that general relativity and the standard model, as our best description of quantum fields, are co-equal. Neither is reducible to or derivable from the other. They are both fundamental descriptions of different aspects of reality.
Wow. Okay, that is a big shift from the usual reductionist school.
It is. And it means the most interesting, the most challenging. The new physics doesn't lie in finding some deeper theory that contains both GR and the SM. Instead, it lies at their interface.
At the boundaries where they meet and interact?
Precisely. It's about understanding the rules of engagement, the laws of harmony and counterpoint, as the analogy goes, that govern how these fundamentally distinct theoretical domains talk to each other.
So what are these domains in the analogy?
In the symphony analogy used in the source, general relativity is like the basso continua of the deep foundational score of space-time geometry. It sets the stage, the structure, the rhythm for everything else.
The underlying beat of the cosmos.
You could say that. And the standard model, quantum field theory, is the rich and complex melody and harmony of matter and forces playing out on that stage. The particles, the interactions, the quantum fuzziness.
And the old quest for a theory of everything.
That's like trying to replace this whole complex orchestra, the bass, the melodies, the harmonies, with a single powerful synthesizer. It might approximate the sound, maybe even very well in some cases, but it fundamentally misses the richness and the emergent complexity that comes from the interplay of distinct parts.
So STP wants to find the rules of that interplay, the harmony and counterpoint.
Exactly. How do the deep notes of space-time geometry interact with the complex melodies of quantum fields? That's the central question.
Okay, but haven't physicists tried to combine them before? What about things like quantum field theory in curved spacetime? QFTCS.
Yes, absolutely. And QFTCS is actually a crucial piece of the puzzle, serving as a kind of prototype or limiting case within the symphonic framework.
How so?
QFTCS treats matter as quantum fields, domain Q, living on a fixed, classical, curved spacetime background, described by GR, domain G. It's a hybrid approach, a semi-classical approximation. And it's been incredibly successful. It led to profound predictions like the Unrow effect.
where an accelerating observer sees heat in a vacuum.
Right. And, most famously, Hawking radiation. The idea that black holes aren't truly black but emit thermal radiation due to quantum effects near their event horizon. Huge breakthroughs.
But you said it's an approximation. Where does it break down?
It breaks down precisely where the interaction between the domains becomes too strong to ignore. Its governing equation, the semi-classical Einstein equation, basically says space-time curvature, GR side, is determined by the average value of the quantum stress energy tensor, QFT side.
The average.
But what happens when quantum fluctuations aren't small? When they're large and violent, like near a black hole singularity or in the very early universe? Or when the energy of the quantum fields themselves becomes so significant that it heavily influences the space-time geometry, the so-called back reaction.
The approximation fails.
The approximation fails. The semi-classical equation just doesn't capture the full dynamics. Furthermore, if you try to go beyond QFTCS and actually quantize gravity itself as just another field interacting perturbatively, like adding small corrections, you run into serious mathematical problems.
The non-renormalizability issue, infinities popping up everywhere.
Exactly. The calculations break down, yielding infinite, nonsensical results, especially at high energies. This has often been interpreted as a fundamental failure of GR at the quantum level.
But STP reinterprets this.
Yes, STP says, hold on, maybe the problem isn't that GR is fundamentally wrong or incompatible with quantum mechanics. Maybe the problem is the method, the perturbative approach, trying to treat quantum gravity effects as small corrections. Maybe the interaction between the gravitational domain G and the quantum domain Q is fundamentally non-perturbative. You can't just calculate it piece by piece. You need a new way to describe the interaction itself.
So QFTCS isn't wrong, it's just incomplete, like listening to the quiet parts of the symphony.
That's a perfect way to put it. QFTCS is the classical limit, or the lowest order term of the full symphonic interaction. It works beautifully when the music is quiet, low curvature, small quantum fluctuations. But for the crescendos, black holes, the Big Bang, the truly extreme regimes, you need the full score. You need the dynamics of the interface itself.
Okay, so this interface becomes the key. How does STP formalize this? You mentioned postulates.
Right. STP lays out 3 core postulates to build this framework. Postulate I is domain sovereignty.
Okay, sovereignty, meaning they rule their own realms.
Precisely. The physical universe is partitioned into these distinct co-equal domains, each governed by its own theory and having its own fundamental stuff, its ontology. First, domain G, or gravitas, governed by general relativity. Its ontology is smooth, 4D space-time geometry. Its laws are deterministic, local. It defines the large-scale structure, gravity, the causal fabric. The shell is a space-time, laying down the foundation.
Got it. And the other?
Domain Q, or quantus, governed by quantum field theory, specifically the Standard Model. Its ontology is quantized fields, particles. Its laws are probabilistic, often non-local. Think entanglement. It defines matter, radiation, microscopic interactions. The violins of the quantum world playing the melodies on top.
2 distinct domains, G and Q. That's postulate 2.
Postulate 2 introduces the harmonic interfaces. This is the crucial step. It states that physical conditions where domain G and domain Q significantly overlap and interact form a dynamical physical entity with its own degrees of freedom.
Not just a conceptual boundary, but a real thing.
A real physical thing, yes. A dynamical entity. Think of black hole event horizons, the cosmological horizon bounding our observable universe, possibly the Planck scale space-time foam, the Big Bang singularity. These are all proposed examples of harmonic interfaces.
And these interfaces have their own physics.
They do. Their dynamics are governed by a completely new mathematical object introduced by STP, the Harmonic Interaction Tensor, IMO.
Okay, a new tensor. Where does it live? What does it do?
It lives on the 3D hypersurface that defines the interface itself. It doesn't exist throughout all of space-time, only on these boundaries. And its job is crucial. It mediates the exchange of energy, momentum, and quantum information between domain G and domain Q. It acts like a transducer or a dictionary, translating between the geometric language of GR and the quantum state language of QFT.
Wow. Okay, so that tensor is the key to the interaction. What's the third postulate?
Postulate 3 deals with emergent phenomena. This is where STP claims to solve the big puzzles. It proposes that phenomena which appear paradoxical or inexplicable when viewed solely from within GR or QFT, things like the black hole information paradox, the cosmological constant problem, the problem of time, are not actually flaws within those individual theories.
Error.
They are emergent properties arising from the dynamics of the harmonic interface. They are the symphonic music produced by the coherent interaction of the two fundamental domains at these boundaries. The paradoxes dissolve because you're looking at the interaction, not just the players.
So the universe isn't just one big thing. It's fundamentally separated into G and Q, governed by their own rules. And where they meet at these harmonic interfaces, that's where the really interesting physics happens, mediated by this ion tensor.
You've got it. That's the core conceptual framework. It separates the domains, but then introduces a specific mechanism for their interaction precisely where they need to interact most strongly.
And the big problems, the paradoxes, are phenomena of that interaction zone.
Exactly. They're not bugs in GR, QFT. They're features of the interface dynamics.
So this harmonic interaction tensor, Imi, it's like the conductor, the rulebook, the translator between spacetime's deep bass and quantum's high melodies. That sounds incredibly important, but also challenging to define mathematically.
It absolutely is. And that's where the real work lies. STP implements this using the language of action principles, which is standard in modern physics. The total action for the universe is proposed to be total SEH for Einstein-Hilbert gravity, plus SSM for the standard model, plus syneraction.
And that last term, syneraction, that's the new piece.
That's the completely novel part. And crucially, it's defined only on the 3D hypersurface of the harmonic interface. It's not integrated over all of 4D spacetime. Its Lagrangian density, lint, which defines the dynamics, depends on fields from both GR, like the metric tensor, and QFT, like quantum field operators, and on this new dynamical field, the ion tensor, which lives only on.
So IM is itself a field with its own dynamics.
Yes, exactly. It's not just a fixed set of rules. It's a dynamic entity. Conceptually, think of it as the transducer. Its components encode how quantum properties, like entanglement entropy on the Q side, map to geometric properties, like horizon area on the G side, and vice versa. It mediates the conversation.
And the big challenge is writing down the equation for it. The lint.
That is the central open problem, yes. Finding the precise mathematical form of lint is key. But STP doesn't leave us completely in the dark. It provides specific criteria that lint must satisfy.
Such as?
It must be local on the interface. Interactions happen at points on the boundary. It must respect fundamental symmetries. General covariance. Laws look the same in all coordinates. And gauge invariance, a key QFT property. Critically, it must have the correct classical limit. In situations with low curvature and low energy density, the full dynamics must reduce to the semi-classical Einstein equation, Kimachis-T's, ensuring it reproduces all the known successes of QFTCS.
So it connects back to what we already know works in less extreme situations.
Exactly. And perhaps most importantly, E must function as an information channel. It needs enough internal complexity, enough degrees of freedom to store the quantum information content of anything that falls across the interface, preventing information loss.
Where might we look for inspiration to build this lint?
The paper suggests drawing inspiration from things like the AD-SCFT correspondence.
The holographic principal connection.
Precisely. AD-SCFT provides a concrete mathematical example where a theory of gravity in a bulk spacetime, ADS, is exactly equivalent, or dual, to a quantum field theory living on its boundary, CFT. In a sense, AD-SCFT already contains a kind of harmonic interface, the boundary, and a dictionary, the holographic map, that translates between the bulk gravity and the boundary QFT. STP suggests that I could be the dynamical field that makes such a holographic relationship manifest in our universe.
Okay, so it's a framework with a big mathematical challenge, but also some guiding principles and potential connections to existing ideas. Now, the crucial part, can it actually solve anything? What about those big, baffling problems?
Right, that's the payoff. The claim is that STP reframes these long-standing paradoxes, not as inconsistencies within GR or QFT, but as natural consequences of the interaction dynamics at harmonic interfaces.
Let's take the big one, the black hole information paradox. How does STP handle throwing that book into a black hole? Is the information lost or not?
STP offers a rather elegant resolution here. The paradox, as you know, arises from the apparent conflict. Quantum mechanics insists information is never lost, unitarity, but Hawking's calculation using QFTCS suggested black hole radiation is purely thermal, carrying no information, while GR's no-hair theorem implies the black hole itself forgets the details of what fell in.
The ultimate clash between GR and QM.
Exactly. STP dissolves the paradox by fundamentally changing the picture of the event horizon. It's not a passive one-way membrane or a point of no return in the classical sense. The event horizon is a dynamic harmonic interface.
So the information doesn't just vanish across it.
No. According to STP, as a quantum system, like our unfortunate book, falls toward the black hole, its quantum information isn't destroyed or lost inside. Instead, it gets transcribed.
Transcribed. On a what?
Onto the degrees of freedom of the harmonic interaction tensor, I, residing at the interface, the event horizon itself. Think of the interface as a kind of memory bank. The energy and momentum of the book fall into the gravitational domain, increasing the black hole's mass as expected. But the specific quantum information, the arrangement of atoms, the story written in the book, gets encoded into the state of the I field at the horizon.
Okay, so the info is stored at the boundary. What about Hawking radiation? Doesn't that still seem thermal and information-free?
SDP reinterprets Hawking radiation too. It's not emitted from the quantum vacuum just outside the horizon as the original calculation. Instead, the radiation is emitted by the interface itself. The harmonic interface, I field, is a complex many-bodied system, and it settles into a thermal state at the Hawking temperature, so it naturally radiates thermally.
But if it's thermal, where does the information go? Is it still trapped on the interface?
No, and this is the key. The information stored in the I field isn't trapped forever. While the radiation is mostly thermal, the dynamics of the interface encode subtle, non-thermal correlations within the outgoing Hawking radiation over the very long timescale of the black hole's evaporation. These correlations are incredibly faint and spread out over the entire lifetime of the radiation, but collectively they carry all the original information that fill in.
So the total state of all the radiation emitted over the black hole's life is pure, not mixed. It remembers the book.
Exactly. The complete radiation state is pure, preserving quantum unitarity. Information is never lost. It's just temporarily stored on the interface and then slowly, subtly released back into the universe via these correlations in the Hawking radiation.
That's actually quite neat. It gives the horizon a physical role, a memory. Does it connect to other ideas people have had, like firewalls or fuzzballs?
It does seem to provide a unifying framework. The firewall idea, which suggested a high-energy region at the horizon, could be interpreted within STP as a specific, highly excited state of the harmonic interface. And the fuzzball concept from string theory, where the singularity and horizon are replaced by a complex, stringy object, could be seen as providing a possible microscopic description of what the degrees of freedom of the I tensor actually are. STP offers the overarching dynamical principle.
Okay, that's potentially one huge paradox resolved. What about the cosmological constant problem, the worst prediction in physics?
Ah yes, the 120 orders of magnitude embarrassment.
Where the quantum vacuum energy predicted by QFT should warp spacetime catastrophically, but the observed effect, dark energy, is minuscule in comparison.
Right. Standard thinking assumes that the zero-point energy of all quantum fields in the vacuum directly contributes to the energy momentum tensor that sources gravity in GR. And when you calculate that contribution, it's absurdly large compared to the observed cosmological constant driving cosmic acceleration.
So how does STP fix this disaster?
It fixes it by fundamentally severing that direct link. In STP, the physics of domain Q, quantum fields, and domain G, gravity, are distinct. The enormous vacuum energy calculated within QFT is contained within domain Q. It doesn't automatically leak over and curve spacetime in domain G.
So the quantum vacuum energy just doesn't gravitate directly?
Not directly, no. The interaction between the domains happens only via the harmonic interface and is governed by the I tensor and its Lagrangian lint.
Okay, so if the QFT vacuum energy isn't causing the cosmic acceleration, what is? Where does the observed dark energy come from in this picture?
STP proposes that the observed dark energy, the tiny positive cosmological constant, is not the QFT vacuum energy at all. Instead, it's an emergent, large-scale phenomenon arising from the dynamics of the cosmological interface.
The cosmological horizon, the edge of the observable universe.
Exactly. That's the largest harmonic interface we know of. The observed dark energy is proposed to be something like the zero-point energy of the interface itself, or a residual tension arising from the constant low-level interaction between the quantum vacuum fluctuations, domain Q, and the expanding spacetime geometry, domain G, at this vast boundary.
Like a subtle hum or a cosmic beat frequency from the two sections playing together on the largest scale.
That's a great analogy for it. It means the value of the cosmological constant isn't something you calculate from first principles in QFT and get catastrophically wrong. Instead, it becomes a fundamental parameter of the interaction Lagrangian lint.
So we measure it, and that tells us something fundamental about the interaction itself.
Precisely. It changes the problem from a calculation failure to an observational input for the new interaction theory. It sidesteps the 120 orders of magnitude problem entirely.
Clever. Okay, one more big one. The problem of time. Quantum time is fixed, GR time is flexible. How does the symphony handle time?
This is another deep conceptual clash. Quantum mechanics uses a rigid external time parameter, like a universal clock ticking in the background, against which quantum states evolve. General relativity treats time as just one coordinate within a dynamic, flexible four-dimensional space-time, where the rate time flows depends on gravity and motion. There's no universal clock.
So how do you reconcile absolute time with relative time?
STP's answer is basically, you don't. It embraces the difference. It suggests that time, like other concepts, might be domain-specific. There is no single universally valid concept of time that applies across both domains seamlessly.
So GR has its time, QM has its time.
Essentially, yes. Domain G has coordinate time, relative dynamical part of geometry. Domain Q has parameter time absolute within its quantum framework driving unitary evolution.
But they have to connect somehow at the interface, right?
They do, and that connection is mediated, again, by the harmonic interaction tensor, i.e. part of its job, part of its mathematical structure, must involve acting as a temporal mapping function. It needs components that dictate how the flow of parameter time for a quantum state evolving on the Q side of an interface relates to the flow of coordinate time for, say, an observer crossing the interface on the G side.
The time translator at the boundary.
Exactly. Which means our everyday experience of a single, smooth, flowing time is likely an emergent approximation. It works incredibly well in our familiar world, far from any extreme interfaces.
Like the smooth river hiding the chaotic molecules.
Precisely. Our macroscopic sense of unified time emerges from these deeper interacting temporal structures. But near an interface like trying to describe what happens precisely at a black hole event horizon, the concept of a single unified time breaks down. You need the full complexity of the temporal mapping function within I.
Wow. Okay, that's tackling some of the biggest conceptual hurdles in physics head on. But the crucial question remains, can we test any of this?
And this is where STP aims to be fundamentally different from, say, current string theory, or LQG. Its proponents argue its primary virtue is its potential testability.
Not relying on reaching the Planck scale.
Exactly. Shifting the focus from those inaccessible energies to potentially observable phenomena occurring at macroscopic or mesoscopic scales, specifically phenomena related to these harmonic interfaces. We don't need to see the individual quantum loops or strings. We need to listen for the unique sounds the symphony makes when the different sections interact strongly.
Okay, so what are these testable predictions? What should we be listening for?
One of the most prominent predictions discussed is related to gravitational waves from merging black holes.
We're getting really good at detecting those now. What's the prediction?
Standard GR predicts that after two black holes merge, the final distorted black hole settles down into a stable Kerr black hole if it's rotating. It does this by emitting gravitational waves in a characteristic ring-down phase, like a struck bell ringing down to silence. After the ring down, GR predicts silence.
Okay, standard picture. What does STP add?
STP says the merger of two black holes is also the merger of their harmonic interfaces. Remember, the event horizon is an interface. This merger is a highly energetic, violent process for the I field itself. After the initial merger and ring down described by GR, the newly formed disturbed harmonic interface, the I field, needs to oscillate and relax into its new equilibrium state. And just like an oscillating object can radiate energy, this relaxing interface should radiate gravitational energy.
So more gravitational waves after the main event.
Exactly. STP predicts faint, high-frequency, exponentially decaying reverberations, or echoes, in the gravitational wave signal after the standard ring down predicted by GR has finished.
Echoes, like hearing the concert hall acoustics after the music stops.
That's a perfect analogy. Detecting these echoes would be direct evidence for physical structure and dynamics at the event horizon, evidence for the harmonic interface. Their specific properties, the spectrum, frequency, decay time, would directly probe the parameters of the interaction, Lagrangian lint. They would tell us about the acoustic properties of the black hole interface.
Has anyone looked for these echoes?
Yes, it's actually a very active, though currently quite controversial, area of research in gravitational wave astronomy. There have been some tantalizing hints in the data, claims of possible echo detections, but nothing statistically significant or universally accepted yet. It's right at the edge of our current detector sensitivity.
But it's a concrete prediction, something we can actively search for with better instruments.
Absolutely. A confirmed detection would be incredibly powerful evidence for STP, or at least for some new physics, at the event horizon beyond classical GR.
Okay, echoes from black holes. What else? You mentioned mesoscopic systems. Could we test this in a lab?
Potentially, yes. There's a growing field exploring tabletop experiments to probe quantum gravity effects, looking for things like gravitationally induced entanglement or decoherence in carefully controlled quantum systems. Now, standard QFTCS makes predictions for how quantum states behave in classical gravitational fields. STP predicts deviations from these standard predictions, specifically in regimes where an interface becomes relevant.
Even an artificial one, like an analog black hole horizon made in a lab using fluids or light?
Possibly, yes. Or even just in situations with very strong gravitational gradients. Consider an experiment with two entangled particles, where one is placed in a significantly different gravitational potential than the other. STP suggests the harmonic interface, even a subtle one induced by the gradient, could mediate a novel form of non-local correlation between them. It wouldn't just be the standard effect of gravity on time slowing down, gravitational time dilation.
It would be something extra, affecting the entanglement itself.
Yes, it might manifest as a violation of Bell's inequalities, a key test of quantum non-locality that depends specifically on the gradient of the gravitational field in a way not predicted by standard QFTCS. Essentially, the I field would act as a new, albeit weak, channel for information exchange between the entangled particles, subtly altering their spooky action at a distance.
Wow. Bringing quantum gravity tests down to the lab scale, that would be revolutionary.
It would be. It's extremely challenging experimentally, requiring incredible precision, but it represents a tangible goal, unlike waiting for Planck scale accelerators.
Okay, black hole echoes, tabletop entanglement tests. Anything on the cosmological scale?
Yes, the third main area is the cosmic microwave background, the CMB.
The afterglow of the Big Bang, how could STP affect that?
Remember, the cosmological horizon, the boundary of our observable universe, is the largest harmonic interface we have access to. Standard cosmology, based on inflation plus GR and the standard model, does an excellent job explaining the CMB's overall properties.
But there are some nagging anomalies, right? Things that don't quite fit perfectly.
There are, particularly some oddities at very large angular scales on the sky, like a potential lack of correlation where standard models predict there should be some. It's like the longest wavelengths, the deepest notes in the cosmic background radiation are quieter than expected.
And STT might explain this.
STP suggests that the ongoing dynamics of the cosmological interface, the continuous interaction between the expanding spacetime, domain G, and the quantum vacuum, domain Q, at the edge of the observable universe, could induce very subtle, very long wavelength correlations in the CMB temperature fluctuations. These wouldn't be the kind predicted by standard inflation. They might appear as a specific type of non-Gaussian signature, a slight deviation from perfect randomness, particularly prominent at those largest scales.
Have we seen hints of this?
Again, it's right at the edge of statistical significance in current data, like the Planck satellite results. Some analyses suggest there might be something there. Others say it's likely just a statistical fluke. We need better data, future surveys.
But it's another potentially observable signature, tying the theory to cosmological data.
Exactly. It connects the fundamental theory of interaction to the largest observable structures in the universe, offering another avenue for testing. Gravitational wave echoes, tabletop entanglement, CMB anomalies, these form a suite of potentially observable consequences.
Okay, so it's a theory with potential solutions to big problems and potential tests. But it's new. It's radical. How did the physics community react? Let's get into that peer review.
Right. The source material gives us a fascinating glimpse into this process. We have comments from 3 anonymous reviewers representing different perspectives and the author's response.
Who's first up?
First was Dr. Evelyn Reed, identified as being from the Institute for Advanced Study, and she was very enthusiastic.
What is she like?
She called STP a bold and refreshing conceptual shift, a masterstroke of philosophical and physical insight. She particularly loved the treatment of the black hole information paradox. She felt the harmonic interface idea, this physical entity at the horizon that transcribes and re-emits information, provided a really intuitive and dynamical picture that could unify previously separate ideas like firewalls and fuzzballs.
So bringing different proposed solutions under one roof.
Exactly. She saw the introduction of the I-tensor not as a flaw, but as a necessary, albeit radical step, comparing its conceptual leap to Einstein's own foundational work. And crucially, she emphasized the clear path towards testable predictions, especially the gravitational wave echoes, as a huge advantage over theories stuck at the Planck scale.
So she saw it as potentially healing the divides in the field.
Yes, she concluded it had the potential to heal the unfortunate segregation in quantum gravity research by offering a new, potentially common, and empirically accessible ground. Very positive review.
Okay, but peer review usually isn't all praise. Who was the skeptic?
That would be Dr. Ben Carter, identified as being from Caltech. And he was, well, let's just say, highly critical.
Uh-oh.
What were his main objections?
He essentially dismissed the work as pre-scientific and based on appealing metaphors rather than rigorous physics. His core critique targeted the Harmonic Interaction Tensor, HAMI.
The show me the math argument. Precisely. He argued that without a concrete, explicitly written down Lagrangian lint for this tensor, without derived field equations showing exactly how it behaves and couples to GR and QFT, it's just wishful thinking. He labeled ISI a deus ex machina tensor.
A convenient invention to solve the problems.
That was his implication. He dismissed the proposed tests, the echoes, entanglement experiments, as a mere wish list, arguing they're meaningless without the underlying mathematical formalism to make precise predictions. In his view, STP, lacking this mathematical core, falls into exactly the same untestability trap it claims to escape. He demanded a concrete calculation, like deriving the Unruh effect's temperature from STP principles, before considering it actual science.
So a very strong critique focusing entirely on the lack of mathematical completion at this stage. No points for conceptual novelty from him.
None at all. For Dr. Carter, the mathematical derivation is everything.
Okay, so we have strong support and strong skepticism. What about the third reviewer? Somewhere in the middle.
Dr. Anya Sharma from the Perimeter Institute offered a more balanced and, I think, very constructive perspective. She found the work stimulating and thought-provoking. She agreed with the paper's premise about the conceptual malaise in fundamental physics and saw value in departing from strict reductionism. While she shared Dr. Carter's concerns about the current lack of a complete mathematical formalism for I.
She didn't dismiss it outright.
No. She made the crucial point that historically, revolutionary conceptual frameworks often precede their full mathematical realization. She used the example of Einstein's equivalence principle, the core idea behind GR, which he grasped conceptually years before he developed the full complex field equations.
So concepts first, math later sometime.
That was her argument. But she didn't just leave it there. She offered a specific, concrete path forward. This was her key contribution.
What did she suggest?
She proposed using the ADS-CFT correspondence as a toy model, or a testing ground for SCP. As we discussed, ADS-CFT is this known duality between gravity in a bulk spacetime, like domain G, and a quantum field theory on its boundary, like domain Q. She pointed out that the holographic dictionary in ADS-CFT, which translates between the bulk and boundary theories, is essentially a mathematically concrete example of the kind of interaction mechanism STP postulates via Aya.
So use this existing mathematical structure as a guide.
Exactly. And she issued a specific challenge to the author, A. Alastair, use the symphonic framework guided by ADS-CFT principles to perform a specific, non-trivial calculation.
What calculation?
To derive the entropy of a known type of black hole in anti-de Sitter space, a BTZ black hole, from the STP perspective, using an ion inspired by the ADS-CFT dictionary. If STP could successfully reproduce the well-known result obtained from the CFT side, it would serve as a powerful proof of principle.
Showing the framework can lead to concrete, correct calculations, even if the full theory isn't worked out yet.
Precisely. It was a brilliant suggestion acknowledging the current limits, but providing a clear, actionable step to build confidence and demonstrate mathematical viability.
A constructive challenge. How did the author, Alastair, respond to all this, especially the critique and the challenge?
Alastair's response, according to the source, was very measured and scientifically minded. He thanked all reviewers for their feedback. He acknowledged Dr. Carter's points, conceding that the current manuscript presented a framework, not yet a fully realized theory with all the mathematical machinery in place.
But did he agree it was pre-scientific?
No, he respectfully disagreed with that label, echoing Dr. Sharma's point about concepts sometimes preceding full mathematical formalization in the history of physics.
And the challenge from Dr. Sharma.
He fully accepted it. Enthusiastically, it sounds like. He stated that tackling that specific calculation deriving the BTZ black hole entropy using an ADS-CFT-inspired if within the symphonic framework would be the immediate next step for this research program. He recognized that succeeding in this would provide that crucial first, non-trivial quantitative result, directly addressing Dr. Carter's concerns about mathematical rigor and providing the proof of principle Dr. Sharma called for.
So he committed to doing the math, starting with that specific problem.
Yes. He stated he would revise the paper's conclusion to reflect this as a primary direction for future work, effectively turning the conceptual blueprint into a concrete, calculable research agenda.
That feels like a very productive outcome from the peer review process, showing the idea is evolving based on feedback.
Absolutely. It highlights how peer review, even with sharp criticism, can refine ideas and push research forward.
Okay, so wrapping this up, we've explored the symphonic theory, why it's needed, its core ideas of domain sovereignty and harmonic interfaces, how it proposes to solve major paradoxes, and its potential tests. What's the big takeaway for someone listening, trying to make sense of the frontiers of physics?
I think the biggest takeaway is the challenge to the decades-long assumption that the ultimate goal must be a single theory of everything based on reductionism.
That maybe the universe isn't a solo performance, but this grand, complex symphony.
Exactly. STP suggests that maybe the deepest truths lie not in reducing everything to one fundamental entity, but in understanding the rich, complex interactions between fundamentally different kinds of physical reality, the reality of space-time geometry described by GR, and the reality of quantum fields described by the Standard Model.
It's conservative in keeping GR in the Standard Model, but radical in how they interact.
Precisely. It doesn't throw out our best theories. It reframes their relationship, and by focusing on the interfaces between them, it potentially brings fundamental physics back towards empirically testable predictions.
Moving the goalposts from the unreachable Planck scale to things like gravitational wave echoes or tabletop quantum experiments.
Yes, it offers a different path, one potentially grounded in observation and experiment in the nearer future. It suggests the deepest mysteries might be solved not by finding entirely new ingredients, but by finally understanding the rules of harmony for the ingredients we already know.
So, a final thought to leave our listeners with. If this symphonic view is onto something, if reality operates through these interacting domains, what else might we be missing?
That's a fascinating question. If we're just now learning to listen for the music produced at these interfaces, black hole horizons, the cosmological boundary, what other subtle melodies or emergent rhythms might be hidden there?
What could understanding these interfaces tell us about the fundamental nature of reality itself, if it's not a monolith but this dynamic interplay?
Indeed. If the ultimate truth isn't a single equation, but this intricate dance between distinct, sovereign physical realms, perhaps this pluralistic view offers a more robust, maybe even a more truthful way to comprehend the sheer complexity and richness of the cosmos. It's a profound shift in perspective to consider.